All right, here we're looking at forces for objects that are moving in uniform circular motion. So just as a reminder, uniform circular motion means that we are not speeding up or slowing down, but as we travel in a circle, the velocity changes directions, right? Here the velocity points this way, here the velocity points that way. As we travel around the circle, here the velocity points that way. As we travel around the circle, here the velocity points that way. And what that means is that the object is accelerating as it moves around the circle. Even though it's not speeding up or slowing down, it does have an acceleration. And as we learned in previous chapters, the acceleration of an object moving in a circle is equal to its velocity squared divided by the radius of the circle. So that means the faster you go, the more acceleration you have, and the smaller the circle is for the same velocity, you would have bigger acceleration. And it's called centripetal acceleration, and this is really, really important because it points towards the center of the circle. So as the object moves around the circle, the acceleration always has the value v squared over r, but it changes directions also. It always points towards the center of the circle. So it's called centripetal acceleration because it points towards the center of the circle. And the other important thing to know is that when an object's moving in a circle, there are no new forces. There is no such thing as a force of circular motion or a centripetal force or a centrifugal force. That just doesn't exist. There are no new forces. So the only forces we're going to have are the same ones we've always had: normal forces, friction forces, tension forces, spring forces, gravity forces, all the same forces we've always had. No extra new forces just because the object's moving in a circle. All right, so with that in mind, let's look at a quick example problem. This problem says a car is going around a corner on level ground. So I'm going to imagine what that looks like from above. So here's my road, and here's my car, and here's the center of the circle. So the car is going around a corner on level ground. That's funny. If the corner has a radius of 50 meters and the tires have a coefficient of friction of 0.877, what is the fastest the car can go around the curve? Would this curve be okay on a highway with a speed limit of 70 miles per hour? All right, so what we want to do is we want to look at a free body diagram for this car, but we want to look at it as if we were standing behind the car watching it drive away from us. So here's the back of the car, and the car's driving away from us. And what are the forces acting on the car? Now, I understand there might be a backwards force of air resistance, and there might be a forward force because the driver's pushing the gas pedal. But those don't matter because it's not speeding up or slowing down. So those forces are going to add up to zero. However, the other forces do matter. The car is touching the ground. So there's going to be a normal force pushing up on the car. And of course, we've got gravity pulling down on the car. We sometimes label that with a W for weight. Of course, that's the earth pulling down on the car using gravity. And then again, if I'm behind the car's turning to the left. Let's now shift over to thinking about the acceleration. If the car's turning to the left, the acceleration needs to point towards the center of the circle. The acceleration is going to point to the left. So there's got to be some force that's pushing to the left. And it's not a new force. It's not a force that we've never seen before. It's a force that we're familiar with. So what force could it be? What forces could be pushing the car to the left? And I'm just going to pause for a minute and let you try to think about what those forces might be. Okay, and then I want you to think about if this was a very, very icy road and the car was coming towards the corner and there was no friction between the car's tires and the road, and right about here, the driver turns the steering wheel, but because there's no friction, nothing happens, and the car just keeps going in a straight line. So what we know is it's actually the friction force that pushes the car to the left. Without friction, the car will never turn left. With friction, the car does turn to the left. So it must actually be friction between the tires and the road that causes this car to turn. And that is actually a static friction force. And we know it's static friction because there's no sliding between the tires and the road. The tires are rolling, but they're not sliding across the road, so it's a static friction force. Okay, so let's look at the rest of this problem then. If we add up all the x components of all, and let's make our coordinate system so that x points to the left and y points up. If we add up all the x components of all the forces, it should equal mass times the x component of acceleration. The only force with an x component is friction, and the whole thing is in the x direction, so it's force of friction. And that's going to equal all of ma, because ma also points to the left. In the y direction, we say if we add up all the y components of all the forces, it should equal mass times the y component of the acceleration. The y component of the acceleration is 0 because it doesn't have an up or down component. And for the forces, we've got a normal force minus a weight. So sticking with the y equation, weight is equal to mg. And this tells us that the normal force is equal to mg. Now, looking at friction, this problem says, what is the fastest the car can go around the curve? Well, the fastest it can go around the curve will only happen when we have the maximum possible static friction force. So we have an equation that says the maximum possible static friction force is mu sub s times the normal force, and that's going to equal m times the maximum possible acceleration, right? If we want the maximum possible acceleration, we need the maximum possible friction force. Okay, and we know that normal force is mg, so mu s mg is equal to ma. The m's cancel. And the last thing we know is that a is equal to v squared over r. Because we're moving in a circle, and this is the only really new thing for these problems, is when we're moving in a circle, the acceleration is v squared over r. Okay, so mu s g is equal to v squared over r. So v is equal to the square root of mu s r g, which for this problem is equal to the square root of 0.877 times 50 meters times g, 9.81, gives 20.7 meters per second. And this problem has two significant digits, so we're going to call that about 21 meters per second is the fastest you can go around that corner before you start to skid, because that will give us the maximum possible static friction. And if I tried to go around the corner any faster, the static friction force would not be strong enough to get me around the corner. Okay, so would this curve be good on a highway that has a speed limit of 31 meters per second? And the answer is, well, no, not at all, because if I was driving 31 meters per second, I would get into an accident. So if I am on the highway, the radius of the curve better be much more than 50 meters. All right, let's go ahead and stop there.